Good evening, student. Today we are diving into materials, but not just how they look or feel, but how they react to the magnetic field. Okay, so our topic is the magnetic properties of material, which is belongs to class 12. Yeah, okay. Specifically, diamagnetism, paramagnetism, ferromagnetism. Okay, these are the important topics today. Okay. To start, imagine a world where trains float silently above the tracks. Yeah. Or where a small chip of metal hangs motionless in the air. Motionless in the air above a magnet. So, this is not science fiction. It is the reality of superconductors, which are the most exotic diamagnetic materials. When certain metals are cooled to extremely low temperature, when metals are cooled to extremely low temperature, they don't just become perfect conductors, they become perfect magnets. So metals becomes into perfect magnets. They totally expel all magnetic field lines. This is a phenomenon called Meissner effect. Okay, Meissner effect. So this perfect repulsion is what allows maglev trains, magnetic leviation train. Yeah, maglev trains. So train above the tracks to leviate. We are going to learn why some materials like the simple copper we use every day try to weakly run away from a magnet. That is, copper is belongs to diamagnetism. Okay, while others like the iron in a refrigerator door stick to it fiercely. So iron belongs to ferromagnetism. Okay, so we are going to learn why some material behave like this and why some material behaves like this. Okay, by the end of this class, you will be able to classify any material based on its magnetic behavior and understand the microscopic reason behind it. Clear? Okay. So let's quickly warm up our brains with a quick 3 question MCQ. I will share the screen. Okay, right. Yes. Right. Now, okay. So this is a quiz icebreaker, which is used to recall your airlet classes, previous classes. Yeah. So first one, the magnetic intensity H inside a solenoid with n turns per unit length carrying current I is given by. Already you know that H is the magnetic intensity, n be the number of turns per unit length which is carrying current I. Then what is the formula which relate the H n I? Which one is correct? Option A, mu naught Ni. Option B, mu naught Ni by psi. Option C, N into I. Option B, option D, B by mu naught. Which one is correct? Any students? Which one is correct? Magnetic intensity H equal to N into I. Yeah, option C is the answer, correct answer. Yes, number of turns into carrying current. Okay, good. Then next one. The quantity that measures how easily a material can be magnetized when placed in an external magnetic field is called. A quantity that measures how easily a material can be magnetized when placed in an external magnetic field. So, suppose if you place one material in an external field, that material responds to that external field. Yeah. So, that means it can be magnetized. So, that quantity, one quantity measure that magnetized characteristic. What is that name? Option A, magnetic permeability. Option B, relative permeability. Option C, magnetic susceptibility. Psi. Option D, magnetic flux. Which one is correct? Which one is correct? Yes. Option D. Okay. KGVB. Any other responses? The quantity measures how easily a material. Note that word. Okay, good. Okay. So option C is the correct answer. Magnetic susceptibility is the correct answer. Yes, very good. Okay. So magnetic susceptibility is the quantity that measures how easily a material responds to the external magnetic field. Yes, correct. And final one, which of the following is the correct relationship between magnetic induction B, magnetic intensity H, and magnetization M? So we can say that magnetic induction or magnetic field. Okay. B, magnetic intensity H and magnetization. Which one is correct? Yes, very good. Yes, option C is the correct answer. Very good. So B equal to mu naught H plus M. Yes, very good. Okay, right. We can check the answer. Yes, first one is H is equal to N into I, number of turns into current. And the second one, magnetic susceptibility. Yes, very good. And the final one, option C is the correct answer. The relationship between B, H, M is the B is equal to mu naught H plus M. Clear? Okay, good. Super. So which is used to recall your earlier classes. Okay, right. Now let's look at the basis for classifying materials. All matter is categorized into three main types. One is diamagnetic, another one is paramagnetic, another one is ferromagnetic. Ferromagnetic. Okay. So based primarily on a value called susceptibility. All the matter is categorized into three main types. Based primarily on the magnetic susceptibility psi. Okay. This is called as psi. CHI. So for diamagnetic, already you know that psi is negative and small. Okay. So these materials are repelled by magnetic field, MF. Okay. Repelled by magnetic field. So MF means magnetic field. Moving from a strong to weak field region. Okay. Moving from strong to weak field region because you applied ununiform magnetic field. So in that ununiform magnetic field, there are the region which has a stronger magnetic field. And there are the region weaker magnetic field. So this material, diamagnetic material, moving from strong to weak field region. And finally, mu r less than 1. Already you know that mu r is equal to 1. Mu r less than 1. Okay. So you have to know that what is psi and mu r. Already you have remember that is psi. This tells us how easily a material can be magnetized. How easily material can be magnetized. Already we saw in the one yeah, MCQ. Okay. So it is a ratio of the magnetism M produced in the material to the magnetic intensity H. It is a ratio of M by H. M means magnetization, H means magnetic field or magnetic intensity. So a high psi means material magnetized strongly. High psi means material magnetized strongly. And mu r means relative permeability. Relative permeability. Okay. Okay. So this tells us how much greater the magnetic field inside the material compared to the field in a vacuum. So this tells us how much greater the magnetic field B is inside the material compared to the field in the vacuum. Okay, vacuum. It is related to susceptibility by a symbol relation, that is mu r, relative permeability is equal to 1 plus psi. Okay, so relative permeability tells us how much greater the magnetic field is inside the material compared to the field in a vacuum. Clear? Okay. Next, paramagnetic. So psi here positive and value small value. They weakly attracted to the external field. So dia repelled, but paramagnetic weakly attracted to the field and moving from weaker region to strong field region. So moving from weaker region to strong field region, and mu r is greater than 1. For diamagnetic, relative permeability less than 1. For paramagnetic, mu r is greater than 1. Okay. Now, last material, that is ferro. So here, psi is very large. Okay. Psi is very large. Magnetic susceptibility very large. And value, positive value, that is psi is double greater than 1. So very, very large and positive. And they are strongly attracted by the external magnetic field. Strongly attracted by the external magnetic field. And finally, relative permeability is double greater than 1. These are the important terms, important notes related to these three type of materials. Okay, right. So you know the sign and the magnet of the psi, you know the type of the material. Okay, if you know the value of magnitude of and the sign of psi, you know the type of materials. Okay, positive means that material, negative means that material, value less than 1, greater than 1, double greater than 1. So which are belongs to some type of material. Okay, right. So now let's spend some time understanding why they behave this way. Okay, some material weakly attracted, some material strongly attracted. We have to understand why they behave this way. So the microscopic origin of these properties, the microscopic origin of these properties. Okay, right. So this is where the physics gets interesting. For example, diamagnet. So already I told you, it repelled. Yeah. Diamagnetic substance, we can say that copper. Copper is the best example for diamagnetism. copper or water. Here, the resultant magnetic moment of atoms is zero. Magnetic moment is zero. Resultant zero. In the absence of external field, we can say that B or H. I will I will tell later. Okay, right. So when an external field applied, it acts like a kick to the electron's orbital motion. Okay, it acts like a kick to the electron's orbital motion. So this change in orbital speed induced a magnetic moment. When an external field applied, induced a magnetic moment. That according to the Lenz's law. So this induced magnetic field opposite to the applied field. சரியா? Okay. Applied field. Opposite to the applied field. Very, very important one. Because of this opposition, the material is repelled. Clear? So remember our McLeod trains. Superconductors are the perfect example showing perfect diamagnetism with psi equal to -1. Completely explaining the field lines. That is Masonry effect. Okay, right. Then next one, paramagnetism. So paramagnetism means yes, weak attraction. Yes, paramagnetism. So weak attraction. Dia means repulsion. Para means weak attraction. So in paramagnetic material, big example, aluminum, oxygen are the some of the examples. Okay. So in paramagnetic materials, the atoms do not have a permanent magnetic dipole. So the atoms do have a already okay. The atoms do have a permanent dipole moments. Permanent magnetic dipole moments. Clear? Okay. So these permanent dipoles are normally oriented randomly due to thermal energy. Yeah. So these magnetic dipoles, that is permanent magnetic dipoles, are randomly oriented due to thermal energy. So that total net magnetization is zero because they are oriented randomly. So suppose if you apply the external magnetic field, EMF, external magnetic field, it provides a big torque, attempting to align the dipoles with the field like that. Okay. So these are the dipoles. So when you apply the field, it provides a big torque, attempting to align the dipoles to the field like that. So this is the field. B or H. Okay, right. So this weak alignment causes the material to be weakly attracted. Clear? So this weak alignment causes the material to be weakly attracted. Temperature dependence. So Curie's law tells us the magnetization is inversely proportional to the absolute temperature. That means Curie law. So here magnetization is inversely proportional to the absolute temperature like that. This means that if you heat a paramagnet, its random thermal motion increases. If you heat the paramagnet, its random thermal motion increases. So its magnetism weakens. So psi equal to C into mu naught by T. So indirectly proportional to temperature and magnetization. So if you increase the temperature, magnetism weakens. Okay. Then final one, ferromagnetism. Ferromagnetism, very strong attraction. So strong attraction, strong. Okay. So here iron or nickel are the example for ferromagnetism. Iron or nickel. Okay. Okay. Or the magnets we deal with every day. Yeah. The key here is the strong cooperative interaction between neighboring atoms, causing their magnetic moments to spontaneously align large macroscopic region called domains. Like that. Okay. So their magnetic moments to spontaneously align in large macroscopic region called domains. So each domain is strongly magnetized. So when external magnetic field applied, these domains already oriented in the field directions like that. Already oriented in the field direction. Grow in size. Grow in size. And domains not aligned rotate to align with the field. Domains not aligned rotate to align with the field. So this result in very strong magnetization. Very strong magnetization. Yeah, means magnetization. So this result in very strong magnetization. If you heat the ferromagnet above its Curie temperature, already you know that Curie temperature Tc. Yeah, Curie temperature. The strong thermal agitation breaks down the domain structure. The material reverts to being paramagnetic. Okay. So if you heat a paramagnet above its Curie temperature, the material becomes into paramagnetic. So above Tc, that is above Curie temperature, susceptibility follows the Curie-Weiss law. Curie-Weiss law. That is psi is equal to C by T minus Tc. This is a Curie-Weiss law. Clear? Okay, right. So now we'll look into simulation. I will share the screen. Second. Okay, right. So here, look at the screen. This is our magnetic property simulation. We have a external magnetization field, H naught. Here you can see that, H naught. H naught means external magnetizing field, which we can control with this slider. Like that. Okay, right. Think of H naught as a field we apply from the outside magnet. Okay, or a current carrying coil. You can see the H naught vector in red color. Yeah, red arrow. Okay. In the center, we have a block of material we can choose different type of material. Copper, copper means diamagnetic, aluminum, paramagnetic, and iron, ferromagnetic. Yeah. Okay. Right. So in this experiment, we are mainly looking at the three important factors. First one, applied field, H naught. The field we apply from the outside. It is constant and points to the right side, like that, right side. And another one, M. Here you can see that M, magnetization. This is the field the material itself creates. Okay, material itself creates. So when we put a material in the external field H naught, the atoms realign and produce their own field M. Already I told you. Yeah. So this is in green arrow. Okay. And another one is magnetic field B. This is a total magnetic field. Is the sum of the H naught and M. Clear? So B is equal to mu naught bracket of H plus M. Already we saw in the third MCQ. Already you know that. So B is equal to mu naught H plus M. Okay. So we see B both inside and outside. So inside dark blue and outside light blue. So the material's response M is defined by magnetic susceptibility. M is equal to psi into H. M is equal to psi into H. Yeah. Here you can see that values. And here you can see that formulas. B is equal to M is equal to and mu is equal to, okay, and the psi is equal to mu r minus 1. Okay. So if psi is positive, M adds to H. That is external field H naught. Okay. Suppose if psi is negative, M subtracts from H naught. Okay. First of all, click the copper. Look at that M vector. Green, it's pointing left. That is opposite to the applied field. We can say that B naught or H naught. So, which is opposite to the applied field. The relative permeability mu r is little less than 1. Mu r is little less than 1. Here you can see that mu r 0.9999, which is less than 1. And psi is minus negative value. So here you can see that minus of 0.006, like that. Result, because M opposes H naught, the total field inside the material is slightly weaker than the outside material. So inside material sound 5 like that, sound 59281. But B outside is sound 59292. So which is very less than. Clear? Then we can choose the aluminum. Here also you can see that M vector. It points to the right. That is same direction as external field. Red color arrow. Yeah. And the relative permeability. Here you can see that relative permeability which is slightly greater than 1. Okay. And psi is positive 0.0022, like that. So positive. So M aligns with the H external field H naught. The total field inside is slightly stronger than the outside. So here also you can see that 759,331, which is slightly larger than the outside field for the aluminum paramagnetic field, paramagnetic material. Okay. For the iron material, you can see the huge difference. We can look at the M vector. It is a huge, yeah. It is pointing strongly to the right, far greater than the external magnetic field. And mu r 5000. Yeah, 5000. Here 5000, which is very large value. Mu r relative permeability. Clear? So and psi is also very high, nearly 5000, 4999. Okay. So the material creates a very strong magnetic field inside than the outside. That's why the arrow mark denotes a larger value than the outside field. So B inside is dramatically stronger than the B outside. This is why a piece of iron is so strongly attracted to the magnet. Clear? So this simulation shows the difference between the material's magnetic response lies in a mu r, relative permeability, and psi, magnetic susceptibility. Diamagnetic, mu r is less than 1. Material weakens the field inside. Okay. Material weakens the field inside. Paramagnetic, mu r is greater than 1. Material slightly strengthens the field inside. And for the final, ferromagnetic, mu r is double greater than 1. The material greatly strengthens the field inside. Clear? Okay. So now we can go into the another simulation, that is Hysteresis loop. I will share the screen. So hysteresis means the material's magnetism, that is B versus H. The B field does not follow the external influence, the H. It depends on its history. So first of all, we have to know the relativity, that is BR. So first of all, look at that screen. Which is A to C. And after reaching the C, it runs back to the D. So at D, H is equal to 0. Already you know that. In the y-axis, x-axis value is 0. So at D, only B value is there, but H is equal to 0. So we magnetize the material to the saturation. That is point C. Point C is the saturation point. Okay. You can see that here also. C is a saturation point. Okay. Right. So we magnetize the material to the saturation and then reduce the external field, H field, back to the 0 at the point D. The B field is still there. Okay. So this remaining magnetism is called the retentivity, that is BR. A material with high BR, like the hard steel on the right, here you can see the hard steel on the right is excellent for permanent magnets. The material with large BR is excellent for permanent magnets. They retain their magnetic field strongly. The next one, coercivity. So here you can see that D to E. Yeah. Okay. So at B, okay, at E, the B is equal to 0. That is magnetic field equal to 0. Now, to remove the remaining magnetism, we have to apply a field in the reverse direction. That is, this is a H positive, this is a H negative. So we have to remove the remaining magnetism. We have to apply the field in the reverse direction, in the direction, negative H. The amount of reverse H needs to kill the magnetic field. Here, 0, magnetic field B becomes 0. Yeah. So this is called coercivity. coercive. Okay, at point E, the soft ion on the left has low value. That is, it is easy to demagnetize. Great for electromagnet. The hard steel has high reverse magnetic field. That is H. That is coercive. So the hard steel has high C coercive. So it is hard to demagnetize. Great for permanent reliable magnets. Clear? Okay. So these are all for this topic, that is Hysteresis loop. Okay. So Hysteresis loop means the magnetic field B inside the ferromagnet does not linearly follow the magnetic intensity H. B does not linearly follows the magnetic intensity H inside the ferromagnet. So, but inside depends on the material's magnetic history. So, retentivity BR and coercivity HC. Retentivity, coercivity. So, already I told you, retentivity means this is a non-zero value of B, non-zero value of B that remains when the external intensity H reduced to zero. Yeah. So, it is also called remnants. A high BR is crucial for permanent magnets. On the other hand, coercivity. This is a reverse magnetic intensity. So H minus, like that, which is required to reduce the internal field to zero, completely back to zero. So B means inside magnetic field, H means external magnetic field. Okay. So it tells us how difficult it is to demagnetize the material. Clear? So hard ferromagnets, example high BR high Hc. This is hard ferromagnet. Example alnico. Which is used to for permanent magnets. On the other hand, soft ferromagnets. Soft ferro. So soft ferro means low BR and high low BR and low Hc. So which is soft ferromagnets are used for electromagnets transformer cores. Okay, electromagnets transformer cores. Okay, so let's apply this idea by solving two problems. I will share the sum problem question. So first question. So this is the first question. A solenoid core material has a relative permeability mu r of 800. The solenoid has 2000 turns per meter and carries a current of 1.5 ampere. Calculate the magnetic intensity H and the magnetic field B inside the core. And you have remember the value, that is mu naught is equal to 4 pi into 10 power minus 7 Tesla meter by ampere. Okay, this is the problem. So mu r 200 turns, 2000 turns, current 1.5 ampere. We have to find H and B. Okay, so the data given, and already we know that is H is equal to Ni. Yeah, clear? So here number of turns 2000 turns per meter. I means current. Here 1.5 ampere. So which gives 3000. 3000 ampere per meter. A solenoid core material has a relative permeability mu r 800, but the solenoid has 2000 turns. So N turns and current. Okay. Now the magnetic field B. Already we know that B equal to mu into H. Yeah. Mu into H. Or we can write B is equal to mu r mu naught into H. Okay. So we have to apply the values in this equation. So B is equal to, already we found that magnetic intensity H. Now we are going to find the value for magnetic field. So mu r mu naught H. Mu r 800 as per our problem, and mu naught 4 by into 10 power minus 7 Tesla meter per ampere, and H we have 3000 ampere per meter. Clear? So this gives approximately 3.016 Tesla. You can verify that, okay, later. B is approximately 3.016 Tesla. Okay. Now we are going to the second problem. Second problem here, based on magnetization M, but we can using the values from problem 1. Okay. This is the problem number 2. Based on the magnetization M, using the values from the problem 1. Already we have a H is equal to 3000 ampere per meter. Okay. And the mu r 800. Yeah. Now we are going to calculate the magnetization M of the core material. Okay. Right. So for this sum, already we have the sum of the important values, that is H, mu r, B, like that. Okay. Right. For the second sum, problem number 2, we know the relation B is equal to mu naught H plus M. So you can rearranging. So M gives mu naught goes here. So B by mu naught, and H goes here. So minus H. And the relationship M and H is psi into H. Yeah. Okay. So then we can write M is equal to, already we know that psi. Okay. So I will write here. There is a relationship between psi and mu r is mu r minus 1. Because we don't have a value for susceptibility, but we have a value for relative permeability. So that we can write these equations. Okay. So M, it is 800 minus 1 H, 3000 ampere per meter. Yeah. So 800 minus 1, 799 into 3000 ampere per meter. So which gives 239700 ampere per meter. This is the value for M. Okay. So which is we can write like that, approximately 2.4 into 10 power 6 ampere per meter. So this is a value for magnetization, 2.4 into 10 power 6 ampere per meter. This is for problem number 2. So now time for a final check of understanding. I will share the screen. 5 MCQ. Okay, once again. You have 4 minutes, okay? So, yes, thank you. So, first one, which of the following is true for diamagnetic substance? Which of the following is the true for diamagnetic substance? Psi is greater than double greater than 1, double greater than mu r. So, mu r means relative permeability, okay? So, mu r, subscript not working in the Google form. That's why I am putting mu r, okay? So, this is a relative permeability. So, what is the value? What is the correct for diamagnetic substance? Mu r is greater than 1, mu r less than 1. Yes, very good. Option B, okay. Diamagnetic substance, psi is, yes, very low and negative. Yes, correct. Negative. Yes. For diamagnetic substance, psi is negative value. Yes. Okay. Good. C. Option C is the correct answer. Very good. Second one, the phenomena of complete expulsion of magnetic field lines from a superconductor when cooled below its critical temperature is called. Already I told you that the effects, yeah. The phenomenon of complete expulsion of magnetic field lines from a superconductor when cooled below its critical temperature is called, yes, option B is the correct answer. Yes, great. Meissner effect. Yes. And above the Curie temperature, Tc, the ferromagnetic material transition into which type of material? Already I told you in that class. Yeah. Above the, above the, yes, option B is the correct answer or option A is the correct answer? Which one is correct? Above the Curie temperature, the ferromagnetic substance, yes. Yes. Purna, yes, correct answer. Very good. So above the Curie temperature, the paramagnetic material transition to, okay, let me check that. Paramagnetic material. Okay, right. Fourth question. In a big H history curve, we saw that the property that represents the value of B when H is reduced to 0. So H reduced to 0, the value of B is called what means? Coercivity, saturation, redundantity, susceptibility. Yes, very good. Okay, option C is the correct answer. Okay, good. Redundantity, yes. And the final one, why is soft iron prepared for making electromagnets? Already I told you, soft iron in our animation, I told you that soft iron, hot steel, yeah. So why is soft iron prepared for making electromagnets? Which one is correct? Okay, right. Okay, so soft iron prepared for making electromagnets means soft iron has low redundantity and low. Yes, option B is the correct answer. And MSMN girls correct. Purna correct. KGBB correct. Very good. AP Stravani correct. Very good. Super. Submit. We can check the answer. Which of the following is true for diamagnetic substance? Psi is negative. The phenomena of complete repulsion superconductor Meissner effect. Above the Curie temperature, the ferromagnetic material transitions to paramagnetic material. Okay, right? Remember that? Okay. Already for the fourth questions, many of the students told correct answer. In BH curve, H reduced to 0. In that case, the value of B is known as the property is known as redundantity. Yes. And the final one, the soft iron has low redundantity, low coercivity, low BR, low HCC. That's why soft iron prepared for making electromagnets. Okay, clear. Very good. Yes, option B is the correct answer. Good. So now please note the homework. This is your homework. Okay. Please write it down. This is theoretical question. This is numerical question. Theoretical question. Explain with the help of BH curve why a material chosen for permanent magnet must have high reactivity, high velocity. Already we saw that. Yeah. Electromagnet, low reactivity, low velocity. Permanent magnet, because electromagnet means temporary magnet. Already you know that about. Okay. So permanent magnet, high reactivity, high velocity. Whereas material for the core of a transformer electromagnet should have low reactivity, low velocity. So you have to explain with the help of pH curve. This is one. And another one, numerical problem. Given the Curie temperature of gadolinium 317 Kelvin, what is the state of gadolinium? Ferromagnetic or a paramagnetic? At room temperature, we can take the 27 degrees Celsius as a room temperature and a high furnace temperature like that 1000 degree Celsius. Justify your answer using the concept of TC, that it means Curie temperature. Convert all temperature to Kelvin first. So write it down. So if you have any doubt, please ask me via the chat box. Thanks. Okay, very important homework. So write it down, please. So please recall our today class session: magnetic material, dia, para, pero, psi, mu or values, and remember that formula, important formula: B is equal to mu naught H plus M. M magnetization is psi into H, like that. Very important. Okay. Okay. I will wrap up the class. Jai Hind, Jai Bharat, Jai Vidyasati. Thank you, teachers. Thank you, students. Thank you all. Thank you. Thank you. Yes, sir.